Okay, so picking up where we left off in the last recording. So I started off, and I still plan on talking about this actually. So we reviewed the expression for the magnetic field for an infinite wire, and we talked about the directions of the field and got the forces and all that. So hopefully we're pretty good there. I started off though wanting to talk about this 2 pi r in the denominator, and it's the circumference of a circle. And then you start wondering, well, first of all, is it really a circumference of a circle? Well, not really, because r is not the radius. Well, actually, maybe it is the circumference of a circle. R is the distance from the current to the point in space where you want to calculate the field. But just focusing on this one right here, so there's r. Isn't that the radius of that circular magnetic field loop? Absolutely. And of course, 2 pi r then would be the circumference of that circular magnetic field loop. And indeed, that's what this is down here. That's where that 2 pi r comes from. Which is really all I wanted to say half an hour ago. But that's good. We need to talk about whatever you need to talk about. Right. So there's that. Now, why am I telling you that? Why do I care? Well, I care because obviously we can do other things with a wire other than have it be long and straight. And so right now, imagine I have a current running through this infinitely long wire, or at least very, very long wire. Okay, I have a current running through it, and the reason I have a current running through it is because I am holding in this hand a AA battery, which you can't see. Okay? And over here, it's connected, on this side, it's connected to something else. I don't know. Okay. And now I'm going to shorten things up and just connect it like so. Okay? In this perfect circular loop. Okay? Now current is flowing because this side of the battery is connected to the bottom of my AA battery. You all believe me that I have a AA battery in my hand, right? Perfect, good. Now I'm going to touch this to the top of my AA battery, and now a current is flowing, right? But once again, we want to talk about, once again, this magnetic field is a vector field, magnitude and direction. So once again, we'll ask about the magnitude. Once again, we'll ask about the direction. Okay, let's start with the direction, because I'm here. Okay, now remember that all I've done is taken this wire, and we know about the direction of its field. It curls around the wire, right? So going towards the ceiling. If the current is flowing up towards the ceiling, grab the wire with my right hand, thumb pointing the direction of the current flow, and my fingers curl around in the same sense of the magnetic field line. Great. Okay. Now if I take this, so you see it curling, yeah? Everywhere? Curl, curl, curl. And if I just take this and form it into a current loop, the current is now flowing like this, but the method of determining the direction of the field is the same. If now the current is flowing like this, up on this side, down on that side, circling around this perfect circle here, grab the wire with my right hand, with my thumb pointing in the direction of the current flow, and my fingers curl around the wire in the same sense as the magnetic field curls around the wire. Okay? But here's the new thing. If I do it horizontally, which is going to be very difficult for me here, but that's all right. Now I can look at it and say, in the region inside, I'll just try it like this. In the region inside the wire, my fingers are pointing, in this case right now, towards the screen, towards you, towards the back of the room. Outside the wire, my fingers are pointing backward, behind me, into the whiteboard, away from the screen. Am I clear here? So in the interior of the wire loop, when the current is flowing like this, I guess is what I'm doing right now. My thumb is pointing in the direction of the current flow. Inside the wire, my fingers are pointing toward you. Outside the area surrounded by the wire loop, my fingers are pointing behind me. Okay? Right now, if the current is flowing counterclockwise as viewed from above. So I look down on it and the current is flowing like this. Then grab the wire with my right hand. Hard to do. Grab the wire with my right hand, and once again, my fingers are in the interior, my fingers are pointing upward, and in the exterior, my fingers are pointing downward. Got it? Mm-hmm. Those are the magnetic field lines, yes. That's right. Not the vectors. Remember, the vectors are everywhere tangent to these circular loops. So these are the field lines. Yes, quite correct. Okay, so and then of course, if you reverse the direction of the current, you reverse the senses of the direction of the magnetic field lines that I just described. In other words, so if the current was flowing clockwise as viewed from above, then the magnetic field line would point downward in the interior of the loop, and it would point upward on the outside. Okay. But a thing I want to draw your attention to is, well, I just made a circle. More like a heart, doesn't it? A Valentine's Day thing. Anyway, if it's a perfect circle, I'm going to draw it in perspective here. I have my current loop, and so what I'm picturing is this, basically. Actually, it's like this, only it's a perfect circle, and then I've just canted it. Yeah. And if I run my current, what I said, counterclockwise is viewed from above, so that would look like this. Get a better pen here. And then behind the whiteboard, it's that way. So counterclockwise is viewed from above. Grab the wire with your right hand. I'm going to grab this side here. Grab the wire with my right hand, thumb pointing in the direction of the positive current flow. Inside the field points. Inside the field points upward. Outside the field points downward. And the thing you need to be clear on is, because all I did was take a long straight wire, which is surrounded by all these circular current loops, and the wire is still surrounded by all those magnetic field circular current loops, but now they're twisted around in a circle, and so you have to draw a million of these, and then I get tired of it, and then I say, now go look at your textbook, or do Google Images or something. Okay. So, then every one of these has its field direction. So, all right, any questions up to this point? Okay. As for the magnitude, it should not surprise you to learn that the mathematical expression for the magnitude of the field of the circular current loop is going to look an awful lot like the expression for the straight line, the infinitely long straight wire, because after all, I created this current loop out of a long straight wire. And indeed, they look very, very similar. Except we have to be careful. This looks really similar, but it's quite different. And my use of capital R here suddenly, rather than lowercase r, is not accidental and not unimportant. I mentioned in, I think, either earlier or in the previous recording, that the actual mathematical process of determining these various magnetic field functions is really, really complicated. If you care, it's something called the Biot-Savart law. And it's a big, scary-looking integral that involves, not only is it a path integral, but it involves the cross product. You have to do a cross product between the current and the differential displacement vector, and then you do that, and then you take the integral of that, and all sorts of crazy geometry, and it's really hard. And my Physics 122 students hate it, but that's what it is anyway. And one aspect of all of that, and the reason I'm telling you this, is that the magnetic field, like the electric field, is different at different places. That's what it means to be a field. And in particular, the magnetic field of a circular current loop for an arbitrary location in space, for any random location, is a very complicated expression, which this is not it at all. This expression is the magnetic field at only one point in space. And the answer, and that one point in space is the center of the current loop. And capital R is the radius of the wire. Not even a vector, I should just draw it. Okay, so there's a lot of similarity between this expression and the field for long straight wire, but they are very different in very important ways. Okay, the important difference is this is the field at only one place, so this is not actually a function, except in the sense that it depends on how big the radius of your current loop is. For this thing over here, long straight wire, this is definitely any distance away from the wire. But this capital R over here is only the radius of your wire loop. So in this case, R would be about, I don't know, 20 centimeters or so, 20, 25 centimeters from the center of this circle out. The other thing you'll notice is, by the way, the pi doesn't appear in here, and that's correct also. And again, I can't go into the mathematical details, but essentially it's a result of the fact that our wire, our source current now is a circle rather than a long straight wire. So this circle also has a circumference involving 2 pi capital R, and when you work out the mathematics, the pi divides out. That's what that is. Okay. Mainly this thing is an exercise in understanding the magnetic field better as a concept. So this is not all that practical because, frankly, how often do you actually care about the field of a single loop? Okay. However, this is the building block of a far more important magnetic field device, which I'm going to pause the recording for a moment, and I'll come back to you. Okay, back, and there's a question. Go ahead. No, there absolutely is. I'm sorry. The question was, or I'm gonna paraphrase your question. The question is, what direction, if any, is there at the center? And let me guess it's the reason for your question. You're looking at it and go, well, there's magnetic field lines from the front going through the center point of the center of the circle, and there's magnetic field lines from the back also going towards the through the center. Do they sort of cancel? Are they going in opposite directions? What do you guys think? No? No? Yeah, I don't think so either. Because remember, the current, so for the front here, I determined that the magnetic field lines inside the wire are pointing upward. Right, so at the center, from the, you got it? Okay, let me finish it up though, since I started it, let me finish it up for the recording anyway. Right, so this is the field from the current in the front half of the wire, if you will. In the back half of the wire, you do the same thing. The current is flowing behind the whiteboard. The current is flowing that way. Grab the wire, curl your fingers around, and until you get your fingers at the, again, the center of the circle, the place where you want to calculate the field. And yeah, as you see, yeah, the magnetic field is also pointing upward there as well. So the net field is upward in both cases. So yeah, good question. Okay, So my last comment was that this magnetic field in this particular device in and of itself is completely unimportant. However, it is the building block of a very important device. And I'll build up to that by easy stages by saying what I did to create that current loop was I took my long straight wire and I simply connected the ends. And by the way, remember, there's actually a battery or some other potential source that's actually driving the current in here somewhere. So there's a AA battery or a Puget Sound Energy in between these two ends of this wire. Okay, but I'm just not going to bother showing it. Okay, but instead of doing this, I could do this. And then connect the two ends. Right? So now I've still got a loop of wire. Now, of course, in this particular case, the radius has now gotten smaller, but imagine that I just took a whole bunch of these and stacked them on top of each other, which is actually what I just did here, right? In any case, the same current is going to run through each so-called turn of this coil. And so we're just going to get, so if in this case I have 4 turns, I can see this in the camera, 4 turns of wire there. And so what happens is you simply multiply this magnetic field. The total magnetic field is simply this magnetic field multiplied by the number of turns you have. Right? That's just superposition. And so this is a single loop, circular loop. Okay, for a coil, which is N circular loops stacked. They all have the same radius. Okay, so that's getting more useful. And then after that, and well, let me show you. This device is more complicated than I really need for this purpose, but I want you to, this is an example of one. So this is actually 2 coils. So here's a coil of wire, and there's another coil of wire, and this is the radius. That's this capital R here. This bizarre looking construct, by the way, 2 coils connected together, is known as a Helmholtz coil, and the reason is that the magnetic field that they produce, each one of them in the region, in this region in here, the magnetic field you can work out for yourself, but it points horizontally. Okay? And this thing is designed so the current that runs through each coil produces a magnetic field that both point in the same direction. And so the 2 reinforce each other. So the field in the middle here, where this little dangly thing is hanging, the magnetic field there is large and uniform and horizontal. Okay. Now I'm not going to go into what this device is, at least not today. But I just want to show you what a coil looks like. Then what you can do is go to extremes, and instead of having just 3 or 4 or 5 or 10 coils, have a whole bunch of them. Connect them across a potential source, and what happens is you get a current that flows in here, and then it goes around and goes around and goes around and goes around all the way through every one of these turns. Finally comes out the bottom, goes like that, and so you have a whole bunch of turns of wire, a whole bunch of magnetic fields. They all reinforce each other. Okay, and the way this thing, what direction does this magnetic field in the interior of this construct, or what direction is the magnetic field pointing? It's hard, it might be hard to tell from the way I've done this, but I think I tried to draw it so that it's flowing counterclockwise as viewed from above. So if I did that correctly, then counterclockwise is viewed from above, so out here, the current would be flowing that way. Okay, I'm off camera here. The current would be flowing that way, and so grab the wire with my right hand, with my thumb pointing in the direction of the current flow, counterclockwise. Yeah, I think the field would be pointing upward in the interior. Okay, and it turns out, and once again, this is a very, very complicated derivation, so I'm not going to do it. But it turns out that the magnetic field that gets created on the inside turns out to be very uniform, very strong, and most importantly, it points everywhere parallel to the axis of these coils. Okay? And this is the important thing, because we take the one coil, stack a gazillion of them up on top of each other in turns of coil, very tightly packed on each other, and it turns out the magnetic field for this thing, which is the magnetic field inside, is constant, both in magnitude and in direction, and is amazingly simple to calculate. It's just mu naught times the number of turns of wire you have times the current you're running through it divided by the length of the device. And such a device is called a solenoid. And I do not know the derivation of that name. And in my remaining 27 seconds, I want to make I want to say one other thing about this. So notice that the B is constant. Does not depend on on the radius of the solenoid, which is interesting. Okay, and then there's just one other thing I can do. So N is the total number of turns you have. L is the length of the solenoid. But if I decide to define little n as simply the number of turns divided by the length of the solenoid, this is called, well, number of turns per unit length. Anyway, then you can calculate B as just mu naught times n times I. And that's typically what is done. Basically, this is basically the turn density, or the number of turns per unit length, number of turns per meter. Okay? And in subsequent classes and subsequent recordings, what I'll do is I will do some examples of calculating this. But frankly, it's dead easy. How many turns do you have per meter? 400 would be a typical value. Run a 3 amp current through it and calculate the magnetic field, boom, like that. Just that easy. Questions? Okay, I'll see you next recording. I'll see you guys tomorrow.